Hello. Yes. This is Wednesday, February 10th. This is ECE 637, model based, digital image processing 1. Hold on, which is way? Oh, I'm going the wrong way. That's the problem. And today I picked up the wrong notebook, so I'm going to have to use the computer slides. But I want to go back and forth because you know I like to draw figures. So let me open this up. So we were doing MRI, if you recall, and now I have to figure out how to fit width. I don't want this non. Okay, somebody explain to me how to do this. Shoot. Am I allowed to open? I don't know why they don't have a functioning download. I don't want to do a download, right? No, I did a download already. And that's desktop, and then I saved it. Save it. Replace. Yeah, okay, but that doesn't, it's silly. Okay, so continue, exit. Okay. But I don't understand. Oh, it's okay now. Why is it doing this thing? Am I allowed to not do this thing?
Can you get it back up with the browser?
Yeah, but I mean, in other words, I'm not allowed to just use.
I can maximize it if you just put it in the browser.
Oh, okay. So I have to open it. So basically, we don't have Acrobat. We don't have a PDF viewer on this computer. Okay. Open. So I don't want to open it. I know that I can't stop myself. Sorry. I mean, so why is it that I'm not allowed to use this? So is this I'm not allowed to make this good. I can't. They won't let me. It won't. I'm not allowed to just use the viewer, huh? Okay. All right. I gotta accept fate as it is. Okay. So I have to open it with Chrome or something.
Yeah.
Or Firefox. This is silly. I don't know why I can't have a PDF viewer on my computer, but okay. Browse as guest. Okay, I should have brought my computer. All right. Oh my goodness. Okay.
You want me to get it up?
Yeah. I mean, what? Yeah, sure.
Right click on that again. Into the open with, I think I saw something else.
Kennedy, you want to do this? Because I'm
document
so
viewer.
sorry. This is why I like physical paper, because it's predictable.
Smart ink document viewer.
You think that's gonna work?
What was it called?
Smart ink
Smart ink.
document viewer.
Okay, there you go.
Is that
You
better?
guys are the best.
I just happened to see that.
Thank you, Kennedy. So sorry. Okay, I'm so sorry. I don't really, yes. Actually, my wife complains that I'm an enabler. I enable all this technology that doesn't work. But, you know, it's fun and you get paid for it. So here's the thing. Okay. All right. Okay, so we've been through most of this. I kind of would prefer to have it viewed as a fit to width. No, okay, fit to width, but then can I page through it? No, of course not. They wouldn't allow that. Hold on. Fit page. I'll do it this way. Okay. Maybe this thing, it'll like it better. Hold on. Oh, this is comical. Okay, I'm so sorry. Okay, maybe if I do this. Oh, there, that works. Oh, wonderful. So we've been through this, right? We went through all this. I don't know what this thing here is doing, but I'll move it. so it's not in the way. Okay, so the upshot is this. Okay, so let me start here. So you want to image a person. So how do you do that? The first thing you do is you, let me see if I can figure out how to do this. Oh, oops. How do I delete? Oh, I hit delete. This is like real time. Is this? No, that's the wrong thing. Okay. Oh, gosh.
Is there a button on the monitor?
Button on the monitor.
Or on the pen?
I think you can see everything I can see, actually.
Or on the pen?
Oh, there might be a button on the pen. Oh, that did something. Okay, I'll do this again. But how do I? There must be a way of deleting, right?
The opposite side of the stylus.
I'll push that little thing there because maybe that'll help. Pen. Do you see an eraser?
Is it just the back of the stylus?
Oh, that would be really interesting. Oh,
Yeah.
you guys are geniuses. Oh my goodness. Okay, now there should be a way of getting something like a hand, right? That would allow me to. No, I guess I'll just do it like this. What's it doing? Oh my goodness. Oh, fit to. Okay. Oh my goodness. I shouldn't be learning this in real time. I apologize. I'll say view 2 pages because they fit on the screen better anyway. Okay.
Yeah.
Excuse me?
Use the pen and just grab the sidebar on the right hand side and just drag it.
Oh, great idea. Except for it doesn't work. Okay, hold on. This is okay. Shouldn't this work? You would think this would work, huh? Maybe the eraser side. Oh, the eraser side works. Okay. Okay. This is like what they call on-the-job training. Okay. So so you have a person, okay, and you want to let me see. Maybe I'll actually grow to like this. You have a person, and you want to image the person, right? Oh, this is the wrong color. Is the only problem. Can I? Oh, let me try this color. You want to image the person, okay? And so the first thing you do. Now remember the frequency. So you can think of the hydrogen atoms as being like little tops that are spinning, okay? Or maybe. Actually, from the point of view of signal processing, maybe the physics analogy isn't so good, but from a signal processing point of view, you can think of them as little oscillators, okay? So little pendulums, okay? Pendula. I don't know if the plural pendulum is pendula. So they're little oscillators, and everybody knows what an oscillator is, right? So, and now with an oscillator, if you hit it, it's like a tuning fork, right? And a tuning fork, when you hit the tuning fork, it goes ding, and you can hear it because it re-radiates the signal, right? And eventually the tuning fork will decay and you won't hear it anymore because the energy is being re-radiated. What you hear from the tuning fork, it may not be very loud, but in some sound, is energy that's being dissipated, okay? So it won't do that forever, but it'll do it for quite a while. Now, no matter what frequency you hit when you hit the tuning fork, it resonates at a characteristic frequency, right? That's determined by that tuning fork, okay? So it doesn't matter how you hit it, it always resonates at the same frequency. If you said have a speaker, and the speaker, you turn up the volume on the speaker, and you hit that like you played rock music, I don't know, and you expose the tuning fork to the rock music, the tuning fork wouldn't resonate because the frequency, the music doesn't have a significant amount of energy at that particular frequency that the tuning fork resonates at. But if you took the speakers and you created a frequency in the speakers that was exactly matched to the tuning fork, you would get it to resonate, okay, at that frequency. So the point is that you can think of the hydrogen atoms in your body as being like different tuning forks. And each one is tuned to a different frequency, right? Now, the frequency of the tuning fork is determined by the magnetic field strength. It's linearly related to the magnetic field strength. Let me go back one. Let's see if I can get this thing to work. And that's this. That equation right there says that the frequency is proportional to this constant L, which is the gyromagnetic constant. This is called the Lamar frequency, and that's called the gyromagnetic constant, times the magnetic field strength. So you increase the magnetic field strength, the frequency increases. You decrease it, and it decreases, okay? Now, what happens then is that, well, you need a very high magnetic field in order for the resonant frequency, in order for the resonance to occur, the physical effect to be strong, basically, okay? So what'll end up happening is that at different field strengths, you'll have different physical phenomena that will occur. I mean, there's a thing called weighting, and if you do MRI research, it's extraordinarily important, but I won't talk about it here. So there are different kinds of weightings, okay? And depending upon the particulars of how you excite the hydrogen atoms, or whichever species you're imaging, you'll get different contrast mechanisms in the tissue. And clinically, that's extraordinarily important because you're basically looking at different stuff, okay? But from a point of view of signal processing, it's not so important because the reconstruction methods are the same either way, okay? So I'll ignore that little issue. It's a huge issue. It's called, and for example, they have things called T1 weighting and T2 weighting and T2 star weighting, and they all produce images which are very different in their characteristics. It would be like having a different filter on your camera. So that's very important to the radiologist, but it's not so important to us right now, so we won't worry about it. But why can't I get this thing to move? Okay, there you go. So the point is now you have this very strong magnetic field that creates sort of the, what you might call the sort of quiescent or ambient level of resonance. But then the magnetic field is modulated, okay? You build coils specifically to modulate the magnetic field. So by modulate, I mean you make the magnetic field a little bit larger or a little bit smaller. So that only changes the resonance very little. But remember, if you're resonating at 127 megahertz, let's say that you're listening to, I like to listen to a radio station, it's called Jeff 92. How many people listen to Jeff 92? It's like an oldie station. It's Jefferson High School's radio station. So they have like, you know, the high school kids, which are funny because they mispronounce things sometimes. And it's Jeff 92, they call it Jeff 92, but it's really 91.9 megahertz, okay? Now, if it's this FM, but let's pretend it's AM, okay? If it's let's say, okay, it's FM, I don't know. So it's your voice, it's audio, right, or it's music. It can go up to, say, 20 kilohertz. It doesn't really go all the way up to 20 kilohertz for FM radio, but unless it's like digital FM, but we don't worry about that. So let's analog FM, but let's say 20 kilohertz, okay? 20 kilohertz is incredibly small compared to 90 megahertz, okay? So 20 kilohertz, that's a factor of what? 4,000 to 1, right? So you can it's less than 1%. It's less than 0.1%. It's less than 0.025%, okay? So it's a very, very, very small modulation of the frequency that causes that signal, but that's perfectly fine because you hear it very clearly when you put the radio on because you can detect very small frequency changes in a carrier, okay? And the way you do that is by demodulating the signal. So what ends up happening is that the resonance frequency in your body changes as a function of position because you've modulated the magnetic field a slight amount. It's very small changes in resonance frequency. So if it's 127 megahertz, okay, it may only be, a few, it might only be like 10 kilohertz difference in frequency, or maybe 100 kilohertz or something. I'm not even sure. You'd have to do the calculation. But that's fine. You can easily detect those frequency changes. So what happens, and you can easily control the frequencies. You see, like, if you just take a hammer and you hit something with it, that's an impulse. You get all the frequencies. That was like when the radio was first invented. The first radio, I guess it was Marconi, right? Had, they just used spark gap. So that's like a hammer. So they just transmitted a pulse over all the frequencies, and they could send dots and dashes, okay? But then people quickly learned that was extraordinarily wasteful, because you're basically just, it's an extremely inefficient way of modulating the signal. You can actually break the channel up into individual frequencies, and you can modulate them separately, and you can be communicating we can all have our cell phones, and we can all talk at the same time, because they're all using different frequencies, okay? So that was a huge innovation. So the point is that you can modulate a signal at a very specific frequency. So this thing is this antenna then sends a pulse, and that pulse is at some very particular frequency. It has a little bit of bandwidth, but it may only be a few kilohertz of bandwidth, or maybe a few hertz of bandwidth. It's probably, if the pulse is relatively short, so like, let's say the pulse is 100 milliseconds, okay? Or if it's 100 milliseconds, it's a tenth of a second. So it might it might only have a bandwidth of in that case 10 hertz, right, or 100 hertz. You can have a very narrow band signal at a very high frequency. So what ends up happening is that the only hydrogen atoms that resonate are the ones in this very particular slice that's where the tuning forks are exactly at the right frequency. Does that make sense? I just want you to get, so you can understand, the equations, and that's fine, but I want you to have an intuition physically as to what's going on. Are there any questions about this? Does that make sense? Because I see some sort of inquisitive looking faces, okay? So, if you have a question, other people would likely have the same question. Okay, so let me see if I can get this thing to work. Okay, maybe it wants to erase right now. I don't know why. I don't know how it decides what it's doing. Okay, so what ends up happening is, so that's what this thing describes. So this thing is the time signal that produces a frequency response like this, right? And that frequency response looks like this. This is 0. This is FC. And now there's going to be a little square pulse. Now I'm drawing this, but in fact, it's not the perspective. Okay? It's not, because this thing here, that distance, is the so-called bandwidth of the pulse. And this is the center frequency. Usually, the bandwidth is much smaller than the center frequency. And the ratio of the bandwidth, okay, so delta F over FC, that's referred to as the fractional bandwidth. So the fractional bandwidth is often, for these RF signals, a very small number. So it might be, the fractional bandwidth might be, 1 part in 10,000, okay? So, but I'm not drawing it this way because it's easier to see, okay? So that's going to be a square pulse in frequency, which means that in time it's a sync. So this thing is called the carrier frequency, right? That's that you modulate, and then the sync function determines the bandwidth here, and then this carrier frequency, the FC, that determines the center frequency. Okay, so you modulate that, you send it out on an antenna, and what it's going to do is it's only going to cause the tuning forks to move. Hold on, if I can get this thing to work again. I'm obviously not understanding this. It'll just cause this single slice here to resonate. And that slice will physically be square because the frequency response was a square pulse. Does that make sense? Are there any questions about that? Because remember, now what it's mapping is frequency to space position along the z-axis. And the reason that's true is because you have three coils. One controls the modulation of the magnetic field along the z-axis, one along the x-axis, and a third along the y-axis. Right now we're assuming the x and the y are set to 0 so that there's no so-called gradient in those directions. The only gradient is along z. Okay? So because there's a gradient at z, the magnetic field changes slightly as you move along z, and they engineer these coils so that the gradient is very close to linear. It's not perfectly linear because nothing's perfectly anything, but it's very close to linear. Okay? So depending upon what the slope of that gradient is, then the change modulations in the center frequency of this RF pulse will cause different slices to be excited. Okay, so basically the tuning forks in those slices will resonate, and that's called slice select. Okay, after you do that, all the tuning forks in that slice will resonate. Okay, and when they resonate, instead of being able to hear it as an audio signal, because it's not sound, it's not a mechanical energy, it's electromagnetic, you'll pick it up on the antenna. And the antenna could be the same antenna you use to transmit, or it might be a different antenna. In this case, these antennas really are more like loops, okay? Like, you guys don't really ever see antennas anymore because they're built into your cell phones, and in your car, they're printed onto the windshield. In the old days, you had real antennas, okay? Like on your car, you'd have like a car that looked like this. And then there was like this antenna thing. And it would always break off for various reasons. But, excuse me?
The routers, their antennas.
Oh, they still have antennas on the routers. Yes, that's a good point. So life is still good. Okay, the other place they haven't, but on your TV, it used to be you had a TV. Okay, nobody really has TVs per se anymore. Okay, and the TV had what they call rabbit ears. Okay, but sometimes for the UHF TV, which was when I was a kid, there were only like 10 channels, but they were mostly all empty. There were only 4 channels that actually worked, okay? There was NBC, CBS, and ABC, and then there was PBS came along later, okay? And each of them in any individual region would be transmitted on particular frequencies. But what happened was, it was really cool. You had a black and white TV. My friend, who was my neighbor, his father actually worked for NBC, so he actually had a color TV. So after school, I would always go to his house to watch the cartoons. But then we got a little box on the top of the thing that had what's called UHF channels, okay, which is ultra high frequency. And that had a different kind of antenna. It was a little loop, okay? And that's the kind of antenna you'll typically see on an MR scanner. But the interesting thing is, too, the picture would never come in right. So you'd have to play around with the antenna, and you'd kind of hold it, and often you'd have to do something like this, like, to get it to work. But anyway, it's a little bit of a separate matter. So anyway, okay. How do I erase this thing? Oh, that's like this. Okay, there we go. Now, so now you have the slice select, and you receive the thing. But you haven't formed an image of the slice. All you did is you resonated, you get the total aggregate response. It's like a tomographic projection in 2D through the person, right? But you don't have any information. So then how are you going to be able to actually form image in the sense of individual pixels How do I get this silly thing to work? Okay. Is that going to work? Okay, there we go. No. Okay, try that. I don't really understand this.
You can always do the arrows on the left like you were doing before.
What did I do?
You can always do the arrows on the left. Go to page by
Oh,
page.
yeah, I could probably do this. There you go. So, okay, so what happens? So now you want to form an image. You want to form an image of, now it's working. You want to form an image of this thing, right? That's the cross section of the person. So how are you going to do that? So what happens is this. You first look at what a single voxel is going to resonate. The intuition here is this, okay? Because I can go through, I mean, I went through the equations and that's fine, but I think, you know, I'm a big believer that that in order to be a good engineer, you really have to understand things in two ways, okay? You have to understand the intuition, and then you also have to understand the math. And you have to sort of be able to align those two views of the world in your mind, okay? That's very important. So if all you can do is the math, I mean, that's great, but it's not good enough, okay? And if all you can do is the intuition, that's great, but it's not good enough. Some people are good at the intuition, and they're bad at the math. And some people are good at the math, and they're bad at the intuition. You know, most people are better at one than the other. So there's some people that I guess are equally good at both. But most people are better at one than the other, okay? So whichever one you're better at, you really should try to work on the other one, okay? Because otherwise, if you're good at the intuition, what you do is you just say things like, you go, oh yeah, it's like we're sort of like little, maybe like the Earth is like an atom in a molecule, and we're really part of a lollipop. I mean, you know, it's like all this good stuff. It sounds really great, but you really can't get the rubber to the road and make anything work, okay? Then the other people are analytical. They go through all these calculations, and they fill up pages and pages and pages and pages. But I can tell you something, which is that I don't care how good you are at that, okay? And you could be very good at it. Some people are like extraordinarily good. But if you don't have any intuition to guide you, you will get to the end and it will be wrong. Because the chances that you can go through 10 pages of calculations and not make any mistakes is like zero, okay? You need the one as an error checking mechanism for the other. So you need to build the intuition, and you need to also be able to do the calculations. You need to be able to do both, okay? So here's the intuition. The intuition is that what we're going to do, okay, these are all resonating. So the, I want to move this thing. These things are all resonating at the same frequency. But now what we're going to do is we're going to apply a gradient, say, in the x direction. When we apply a gradient in the x direction, what will happen is that the hydrogen atoms over here will increase their frequency. It would be like if you had a violin, okay? And you pluck a violin string, right? It has a resonant frequency. But if you move your finger on the fret, that frequency will change, right? So it's not necessarily a fixed frequency if you change the conditions, the boundary conditions on the string, right? So the same thing happens here. Yeah, a tuning fork is like designed so it only oscillates at a single frequency. But even there, you could change this frequency a little bit if you, for instance, change the temperature of the room, okay? But some things like a guitar or a violin are designed so you can easily change the frequency. And that's how people get like vibrato, right? Because they move their finger back and forth and the frequency goes up and down, right? Here what you do is by changing the magnetic field slightly, you will change the frequency at which that thing is resonating, right? And if you make the magnetic, if you have a linear, your magnetic field goes like this, so you have a magnetic field like that that has a gradient, then the frequency here will be higher than the frequency there. So intuitively, if you took the Fourier transform of the signal you received, then what would happen is that the responses from over here would map it to higher frequencies than the responses from here, right? Does that make sense? So intuitively, if you apply a linear magnetic field gradient across this thing, the different pixels will have different resonant frequencies. Now that only works in 1D, so it still doesn't give you a 2D representation. If you also apply a gradient magnetic field that way, then this will resonate at a higher frequency than that, right? So the trick here is this. You apply a sequence of different magnetic field gradients, and then you take the Fourier transform, and from that you should be able to reconstruct the image in 2D. That's the intuition. Are there any questions about that? Yeah.
And so when you're changing this frequency in the x direction, there's a way to tell I changed it in the x direction versus the z direction?
Is there a way to tell? Well, remember, you have 3 distinct coils. The one coil we already used and now we're finished with. We're leaving it alone. But we have 2 separate coils which independently control the gradient along the x and the y dimension. So we have control of that.
But the signal itself, you're just getting one frequency. You're not getting a frequency for each axis.
No, you're actually getting multiple frequencies. Okay. Initially, you only got one frequency because initially, when you did the slice select, everything was resonating at the same frequency. But then after you do the slice select, while it's still resonating, you start changing the gradients in the x and the y dimension. And then what happens is that the different hydrogen atoms at different physical xy locations start resonating at different frequencies. And you can separate those frequencies by taking a Fourier transform. So basically, you're going to use the Fourier transform to form an image. Does that make sense? Yeah.
So at first you do the slice to get like the XY, like a chunk of XY.
Yes.
But why do you set the X and Y gradient?
Well, because, you don't really have to set it exactly to 0, although there's no particular reason to set it to anything else. And if you didn't set it to 0, what would end up happening? Let's say you set the y-axis gradient to not 0, right? And then what would happen is your selected slice would be angular. In fact, they do that. Like sometimes when they want to image in the brain, they don't necessarily take slices which are perpendicular. They might take slices which are like this, in order to avoid certain structures that might create distortions in the image, right? Sometimes they may choose to not take their slices vertically. Exactly.
After you do the slice, so that you're not cutting that part of the human body, right? So,
yeah. So let me reword this in a different. It's a good question, okay? But let me reword my answer. Sometimes it's good to say things multiple ways. So this slice represents a point at which the magnetic field is constant, right? Because all those things resonated at the same frequency. So if the gradient if you only have a z gradient, then this slice will be vertical. But if you have any x and y component to your gradient, then the slice will not be vertical because basically these are like affine manifolds. They're like subspaces in which that function, the magnetic field, is constant. By the way, let me reemphasize that we're treating the magnetic field as if it's a scalar. It's really a vector. But our assumption is that the magnetic field direction is constant and that only its magnitude changes. Did I answer your question?
so my question was, so after slice select, you have to modify the XY.
Yes. So you first do a slice select. Then while the things are still resonating, you can't wait too long because then they'll start to decay. But while they're still resonating, you start changing the x and y axes
So that
of the magnetic field gradient. Right.
Won't change the slice back.
No, it won't change the slice because, no, that's a very good question. Because what happened is these are the only ones that are physically resonating. So the actual atoms presumably are fixed in their location. If it's the bloodstream, obviously the blood might be moving. But let's say the tissue is rigid, okay? Then whichever atoms are resonating, they are fixed in their physical location. But when you change the magnetic field, you'll change the frequency at which they're resonating. So to think of it like you have many little tuning forks, molecular tuning forks. The tuning forks don't physically move, but as you change the magnetic field strength, their frequency at which they oscillate shifts. Just like a violin. Okay, make me think of it as trillions of quadrillion, huge numbers of molecular violins, and the magnetic field is like your finger on the fret of the violin. As the magnetic field strength changes, the frequency of the string's vibration will shift. Yes.
So basically taking the slice select would be like plucking the string of a guitar, like one of the strings.
Yes,
And then
exactly.
X and Y would be putting it down, so the other strings aren't moving at all still. It doesn't
Precisely. No, the analogy is beautiful. Okay. I know some of my analogies are not always good. I have lots of plentiful analogies, but not always good ones. But the thing is that that's an excellent one. I mean, because, yes, so the slice select is like plucking the string, okay? You have to pluck it. If you didn't pluck the string, it's not going to vibrate. You have to put energy into the system. But the magnetic field shifting is like moving your finger on the fret. Once it's vibrating, now you can shift the frequency of vibration. Is that helpful? Because the equations can be dry. You should understand them. It's essential to understand them. You need to be able to do both. Some people are like, oh, I don't need the equations. I have this deep intuition. I mean, like that only goes so far too, okay? Because it sounds good. And if you're like a person who's an intuitive person, that's terrific. I mean, I think it's wonderful. I mean, it's super helpful. It's great. But that's not an excuse for not being able to get the right answer when you do the calculation, okay? So you need to do both, right? Yeah, I'm not forgiving on that stuff. You got to just think, and doing the right, if you're not a person who is good at the calculations, you know what the key is to getting good at calculations? It's not an answer that people are going to like. Practice, okay? There's nothing that gets me more mad, okay, than when somebody says, I'm not good at math, okay? That's really annoying to me, okay? That's a ridiculous statement. Anybody should be good at math. It just requires practice. And you might find it annoying, but if you do it enough, eventually you won't find it annoying, okay? But you can't just do it on simple intuition. You got to be able to get the right answer to the calculation, okay? So I have no sympathy. Sorry. Okay. Now, sorry, I apologize for my strong opinions on that issue. Here's the thing. Okay, so yes, so you need to be able to both. So now I gave you the intuition. The intuition is that now what we're going to do is shift the magnetic field in the different directions, and that's going to allow the different things to resonate at different frequencies, so we'll then take the Fourier transform to reconstruct the image. Now that's the general concept, but then how do we actually do that, okay? This is the math. I went through it last time, but let me go through it now again after having explained intuitively what it means, okay? So in order to derive the equations, when you're doing this kind of calculation, it's best to do it one step at a time, okay? To peel the onion a layer at a time, right? And by the way, one of the key issues in the peeling of the onion is not to panic, okay? Like people sometimes will get overwhelmed by complicated problems. Don't get overwhelmed. You have to have a sense of confidence, okay? That you just are going to plow forward and not give up until you get the answer, okay? So you start off by, so we do the simplest case, one voxel. And this is one thing engineers are very good at. Engineers are very good at taking complicated problems and breaking them down to smaller and smaller pieces until they can do it, okay? It's an amazingly effective strategy. So you have one voxel. Okay, so the one voxel looks like it's radiating like this, where phi of t is the instantaneous phase, okay? And remember, I said the phase, the derivative of the phase is the frequency, okay? Because if you have a constant frequency, it looks like this. 2 pi fct, right? So if I take the derivative of the phase with time, I'll get the frequency. I'll get the frequency times 2 pi because it's in radians. But the key idea, and it's not exactly intuitive in my opinion, is that the derivative of the phase is the frequency. So if the derivative of the phase is the frequency, that means the derivative of this phi is got to be the instantaneous frequency. Because remember, the frequency is going to be changing, right? Because we're going to be changing the magnetic field. That's why we have to write it down formally like this. So we take the instantaneous magnetic field times this L, which is a constant. L is the gyromagnetic constant, okay? So now we can recover the phase by integrating the frequency. And then what happens is this magnetic field really has 3 components. It has, this is sort of the background level of magnetic field caused by the fact that we have a 3 Tesla magnet. And these are the gradient magnetic fields that you have from the 2 different coils that you're changing. The third coil along the z-axis, you're not changing. You're leaving it fixed, okay? Now, then I can derive these 2 expressions for kx and ky. You can say, well, don't worry about what they mean right now. Whatever they are, they're just that, okay? It's just mathematically, that's what they are, okay? So you integrate. So the k is the integral of the gradient for x, and ky is the integral of the gradient for y, okay? But basically, it just comes down to this expression right here. Now, the key thing that's very important is that it's a linear function of x and it's a linear function of y. And the reason it's a linear function of x and y is because the gradient coils were designed to produce linear gradients. That's an approximation, but it's a pretty accurate approximation, okay? So now what happens is you say, okay, the received signal, okay, so we plug the phase expression in, and this becomes R of t. So this is the received signal we get from a single voxel at location x, y in the slice. This thing now is the carrier frequency. The carrier frequency is carrier frequency is like when you have Jeff 92 at 91.9 megahertz. The carrier frequency is 91.9 megahertz. And when you demodulate, but it's well known how to get rid of the carrier. You take the carrier, the signal you receive, and you demodulate it. There's well-known techniques for demodulating the signal, removing the carrier, and then you just get this signal right here, okay? So now we have to integrate over the volume to get the entire received signal. If we integrate over the volume, we're integrating over x, y. Okay, so now is where the magic occurs. Because this integral over x, y, this thing looks like a Fourier transform. Does that make sense? This thing looks like a Fourier transform because where this thing, kx is what we were calling u, and ky is what we were calling v. Right? So, if f is the Fourier transform, all this thing is, it looks like the Fourier transform evaluated at, oh, there's a minus sign missing there. So I have to account for the minus sign. I have a minus kx and a minus ky. And then it's modulated on a carrier. But we know how to remove the carrier. I won't go into that, but that's standard technology for electrical engineering. Your radio or your cell phone does that all the time. So we remove the carrier. Physically, you can't actually multiply by this complex number, but there's a simple analog circuitry that you use to remove the carrier. It's a well-known thing. And then so essentially what happens is that you receive this signal here, where kx and ky are defined like this. So at a particular time, the demodulated signal will be a complex number, and that complex number will be the Fourier transform of the 2D slice evaluated at minus kx and minus ky. Does that make sense? Does that make sense? And remember, the other way of thinking that, okay, so this sort of popped out magically out of the equations, but the underlying intuition is that as we modulated the magnetic field, then the different atoms oscillated at different frequencies, and we could separate out those different frequencies by taking the Fourier transform. So the Fourier transform is actually going to be the inverse Fourier transform, because now we're going to reconstruct by taking the inverse Fourier transform. Okay, so now the problem is that, okay, so what happens is that you have kx and you have ky. So at any particular time, you'll measure a complex number associated with with some particular value of kx and ky. This is a complex number you're going to measure here, okay? Because the Fourier transform is complex. And then the question is, well, what points can you measure? Well, you can move around space by changing the value of kx and ky, and then you will move around the space. So you need to measure the Fourier transform of the person. So when you get an MRI scan, the scanner is measuring your Fourier transform. It's a little scary, okay? I'm not sure I want anybody measuring my Fourier transform, but that's what it does, okay? So the question is, what values of your Fourier transform is it going to measure? Well, the most obvious thing is just to go like this, right? Why not? Sort of like that, right? You can scan through the Fourier transform like that, okay? And not necessarily the best thing, but it's a reasonable thing, okay? So to do that, what you can actually control are gx and gy, the gradients in the coils. How do you modulate the gradients in order to scan through that space? Then what you'll do is you'll take the measurements of the Fourier transform in all those places. After you, in raster order, you'll take the inverse Fourier transform and you'll reconstruct the image, okay? Does that make sense? Now, here's the thing that's kind of cool. If you have, I'm just testing my drawing skills here. Does anybody know what that is?
Vacuum?
It's a vacuum cleaner. Yes, you get an A, okay? He's my favorite student. Okay, here we go. And the vacuum cleaner has a cord. And here's the wall. Now, any engineers by their nature tend to be a little lazy because they want to do the minimum, okay? I call it efficient. My wife calls it lazy. Okay, that's the plug in the wall, okay? So anybody who doesn't feel like walking over, and don't do this, I'm not endorsing it, okay? But if you happen to have ever done this where you're vacuuming and you didn't feel like walking all the way over and pulling the plug out, so you just pull in the cord, right? What happens? Particularly if the lights are dim. And you of course do it while the thing's still running. So the vacuum cleaner's running and you pull the socket out of the wall. What happens?
It stops.
Excuse me? It stops running, yes, for sure. You are definitely an electrical engineer. What else happens?
It bugs.
You get a spark, right? Everybody knows this. No, you don't know it because you haven't done it. I'm not endorsing it. Don't perform this experiment. But if you happen to have done it anyway, you may have noticed that you get a spark, right? You get a spark. So you get a spark. Why do you get a spark? Because you're dumb, right? Yes, okay. But why do you get a spark? What's the electrical engineering explanation for the fact that you get a spark? Because you can pull the plug out of the wall, but you pull other plugs out of the wall, you don't get sparks, do you? There's still current flying. Why would you get a spark? There's a very high inductive load, okay? The motor in the vacuum cleaner is a gigantic inductor. This is a metal bar, okay? So there's an enormous amount of energy stored in the inductive motor, right? So when you pull that out and you stop the current, what happens to the voltage? It spikes because the voltage is equal to the inductance times the derivative of the current with time. I'll let you go now because we're out of time, but I'm going to let you think about that, and then we'll finish it up on the next lecture because we were having a lot of fun today. Okay, bye.